Hey everyone, and welcome to the Explainer. Today, we're heading out on a pretty fascinating mathematical journey. We are going to completely strip away that math anxiety so many of us feel and finally unmask what logarithms truly are. Look, if you've ever stared at a math problem and just felt a sinking sense of dread at the sight of those three little letters, LOG, trust me, you're absolutely not alone. But by the end of our time together, you're going to see them not as some weird obstacle, but as a brilliant time-saving superpower. I mean, let's acknowledge right off the bat that the word logarithm just sounds terrifying, right? It sounds incredibly archaic, like something only an advanced theoretical physicist would ever touch. And we really need to tackle that elephant in the room straight away. The term actually comes from a Scottish mathematician named John Napier. He mashed up the Greek words logos for ratio and arithmos for number. So, ratio number? Yeah, still sounds kind of complicated. But what if he told you this whole intimidating concept is actually hiding a super simple, everyday mathematical idea? Okay, here is the big reveal. The secret identity of the logarithm is simply this. A logarithm is just a power. That is literally it. Because of some quirky historical reasons, people just don't use the word power like they probably should in this context. They use this made-up, intimidating word instead. But from now on, whenever you see the word log on a page or a screen, I want you to just instantly translate it in your head to power or exponent. When we look at the formal definition, that translation makes things incredibly simple. When you see log base b of x, all you are doing is asking yourself one simple question. What power of base b gives you the answer x? So for example, if we look at a really simple one like log base 2 of 8, we're just asking what power of 2 gives you 8? Well, 2 times 2 is 4 times 2 is 8, right? So that's 3 2s. The answer is simply 3. Log base 2 of 8 equals 3. See? It's just a power.
Section 1. Saving science from multiplication.
So, now that we've unmasked what a logarithm actually is, let's travel back in time for a second to the Renaissance. During the 1400s and 1500s, science was just exploding across Europe. Scholars were collecting massive amounts of data about the world, the stars, you name it. But to actually analyze this data, they had to do all these massive arithmetic computations entirely by hand. Adding long lists of decimals, I mean, it's not fun, but it's totally doable. Multiplying long lists of messy decimals, though, that is downright horrid. Scientists were literally drowning in tedious manual multiplication, and it was single-handedly holding back global scientific progress. To fix this, John Napier, along with his colleague Henry Briggs, came up with logarithm tables. Napier figured out this highly complex method, which originally involved imagining particles moving along infinite and finite lines, kind of wild, that essentially turned multiplication problems into addition problems. Briggs then helped simplify all of this into neat, published tables. And the best part? Scientists didn't even need to understand how the tables were made. If they wanted to multiply two nasty numbers, they just look them up in the table, add the table values together, and then look up the result backward to find their answer. It was a complete game changer, a mathematical hack that quite literally saved science. Section 2. The Laws of Logarithms. To truly understand how this magical hack works, we've got to look at the core mathematical laws that make turning hard math into easy math possible. The first is the product's law, and this is Napier's original trick. The logarithm of a product, meaning two numbers being multiplied together, is equal to the sum of the logarithms of those individual numbers. In plain English, it turns multiplication into addition. Taking the log of m times n is exactly the same as taking the log of m and simply adding it to the log of n. And you know, this logic perfectly extends to other operations too. The quotient law does the exact same thing for division. It turns fraction division into simple subtraction. So the log of m divided by n is just the log of m minus the log of n. And then there's the power law, which is incredibly useful. It says the logarithm of a number raised to a power lets you take that exponent and just bring it right down to the front as a simple multiplier. Log base a of m to the power of n becomes n times the log base a of m. You're essentially just shaking the exponent down to ground level. Section 3. The base changing formula. Now, these laws are incredibly powerful, provided you're working with friendly bases. But what happens when you have a logarithm with a base that's just a nightmare to work with? Or what if you're trying to combine multiple logarithms that all have totally different bases? Thankfully, there's a brilliantly mechanical rule called the base changing formula that lets you pick a brand new base, literally any base you want. You just start with your original log, let's call it log base a of m. You choose a new base, say base b. Then you create a fraction. Take the log of your main number m with your new base b, and simply divide it by the log of your old base a, also using that new base b.
Let's actually see how these numbers swap places in practice. Suppose we want to evaluate log base 4 of 64. Now, maybe base 4 just isn't working for us, and we'd much rather use base 2. So, we put the main number, 64, on top. We put the old base, 4, on the bottom. And then we just attach our brand new base 2 to both of them. So log base 4 of 64 becomes log base 2 of 64, divided by log base 2 of 4.
Let's finish the math here. The top is log base 2 of 64. What power of 2 gives 64? The answer is 6. The bottom is log base 2 of 4. What power of 2 gives 4? Well, that's 2. This changes what might have been a really tricky problem into just 6 divided by 2, which easily gives us our final answer of 3. And if you check the original problem, 4 to the power of 3 is indeed 64. The formula just works flawlessly every time.
Section 4. Why logs still matter.
Okay, so since we all carry high-powered calculators in our pockets these days, you might be wondering, why do we still care about this centuries-old math trick? I mean, multiplying decimals isn't exactly a struggle for us anymore. Well, the answer lies in modern algebra. If you take an equation like 7 to the power of x equals 5 to the power of x plus 2, solving that without logarithms is virtually impossible. Variables that are stuck upstairs as exponents are just stuck. But by hitting both sides of the equation with a log, we utilize that power law we talked about earlier. It allows us to shake those variables down to the ground level, turning them into simple multipliers that we can easily solve using standard algebra.
When we do this sort of modern calculation, we usually rely on what's called the common logarithm. This is just a logarithm with a base of 10. Actually, you'll notice on your calculator there's a log button that doesn't mention a base at all. That is the common logarithm. It defaults to base 10, which pays homage to Henry Briggs, since he pushed for base 10 logs, and of course your standard base 10 number system.
Aside from solving equations, logarithms also give us a way to conceptualize ridiculously massive numbers without our brains just melting from endless strings of zeros. We can easily wrap our heads around a million. That's a 1 with 6 zeros, or 10 to the power of 6. A billion is 10 to the 9th. But when you get to something like the estimated number of molecules in the universe, it's 10 to the power of 80. Writing out 80 zeros is just absurd. But expressing it logarithmically, by just focusing on the power, allows us to handle, store in computer memory, and mathematically manipulate the very scale of the cosmos with total ease.
And this exact concept of focusing on the power is exactly how the Richter scale works for measuring earthquakes. The forces involved in earthquakes are massive, large-scale numbers, so we use a logarithmic scale to represent the order of magnitude. Meaning, an earthquake measuring 6.2 on the Richter scale isn't just slightly bigger than a 5.2. Because it's a logarithmic base 10 scale, that jump of just 1.0 actually means the 6.2 earthquake is 10 times more forceful than the 5.2. A 7.2, that would be 100 times more forceful.
So logarithms are not just some dusty, archaic Renaissance hack meant to torture students in algebra class. They are literally the language of exponential growth, the key to unlocking variables trapped in the attic of an equation, and the fundamental tool we use to measure the extreme forces of nature. Next time you read about an earthquake tremor or look up at the vastness of the universe, ask yourself just how much power is really at play. Because thanks to John Napier and the logarithm, you actually have the math to figure it out. Thanks for joining me on this explainer, everyone. Keep learning and keep asking questions.